Drago will tell us about causality and fairness.
Okay, thank you very much for having me here. I want to continue in a similar vein as some of the talks earlier today, and I want to say about how causality relates to calibration. So, oh, right, that as well. You have to subscribe to the YouTube channel, of course. So this is joint work with Elias Barenboim, and I'm a postdoc at Columbia Computer Science. So I want to share the references for the paper that we wrote on causal fairness, and also you can have a look at our ICML 2022 tutorial in case this talk interests you. So what I want to begin with, a basic setting in which we're operating, and a lot of the things that we're talking about today, or sorry, this week, are somehow related to this workflow. So basically, we have the real world at the current time, at time t, and what we're doing, as often in data science, machine learning, computer science, we're collecting data from this world, right? And I think Frauke had a very nice talk about all the things that can go wrong in this process, and so on. So after this, of course, once we've collected the data, the typical thing we do is we're going to plug this into some automated system, right? And the question that I'm trying to ask here, and I think it's very related to Cynthia's talk earlier, is so what happens when we start deploying predictions from this machine learning system? Is this gonna yield something that we consider to be unfair, or is this gonna yield something that we consider to be fair, right? This is sort of the fundamental question that I'm trying to ask. And of course, this is somehow the machine learning tools that we build are going to shape the world in the future times, right? This is one of the assumptions. So we need to be careful in this process, right? And we need to be careful about what we're doing. Okay, and I think the main punchline that I have for first sort of a key point that I want people to take away, and I think Cynthia was hinting at this in her talk, is that the current reality is pretty bad. And if you open up applications, and I think some people have tried to do this, you will find all kinds of bias that is not looking very good. I'm going to talk about some medical data that we have looked at Columbia, from the Columbia Hospital, and from these large-scale insurance data sets. And I also want to mention a couple of stories from economics and econometrics that are well known. And I'm going to say why the law itself also tries to limit some of these discriminatory effects. Okay, so I want to talk in the context of medicine. I want to talk about diagnostic delays. I'm going to say in a second what that means. I want to talk about allocation of respirators and intensive care units. This is something that I'm personally very interested in. And in the context of economics, just to give another example, I want to talk about the gender pay gap, which has been studied thoroughly in the economics literature. I also want to talk about the phenomenon of redlining, and I want to mention that briefly. And within the law, I just want to say something about the disparate treatment and disparate impact doctrines that are somehow related to this whole story. So across a wide range of health and social sciences, we do have evidence that the current reality is quite biased. And I want to start with the story of diagnostic delays. So basically, what we've looked at, we looked at Crohn's disease, and basically, it's sort of, for the context, it doesn't even matter what the disease is. I'm going to say in a minute that how this translates to other diseases. But basically, you can take patients that are diagnosed with a specific condition of the gut, and what you do then, you align these patients, right? So we're looking at the cohort of people that have received the Crohn's disease diagnosis, and what you do then, you go back in time and you try to understand when these people first started complaining about their symptoms. And what you generate through this, if you take the time between the appearance of the first symptom and the diagnosis, this is what in medicine people call diagnostic delay, right? And the question is, how large are these diagnostic delays, right? And are they different between different groups? And what we're seeing, and this is two very large databases, what we're seeing, so here I call it total variation. I'm taking the conditional difference, so I'm taking the average diagnostic delay for men, and I'm subtracting the average diagnostic delay for women. What you can see is that there's a difference of around 70 to 80 days that women wait longer for their diagnosis, right? So there's something substantially different going on for the two groups in this case. And what you may say, and if you talk to anyone who's working with this disease, they're going to come up with a bunch of explanations about why this is. Crohn's is specific in this and that way. And the question is this really the full story? Is this just one disease? Well, the good thing is in the world of today, there's loads of data, right? And what we can look at 100 different diseases. We can look at chronic diseases, acute diseases. We can look at all kinds of different things. The same pattern is there. And if you look at this plot, I'm not sure how well you can see, but this difference is sort of everywhere. So there's not even single condition where you can say, oh, this does not hold.
Sorry. What's blue and what's purple?
So the purple is how long women wait for their diagnosis on average, and the other color is how long men wait. So in some sense, there's sort of a yes. Sorry, I'm colorblind, so it's hard to answer that question actually. But in any case, the conclusion is the same as for Crohn's disease across a range of different examples. And that's sort of first example in medicine. Okay, we have a huge bias, right? And what I want to go next, I want to go to allocation of respirators, another medical context, right? It's slightly different. We're not talking about diagnosis here. We're talking about some kind of treatment decision. And this was sort of very prominent during the COVID pandemic, right? A lot of people needed respirators. And the question is, how do you allocate respirators if you have some kind of shortage, right? And the question is there a difference between men and women when you're doing this process? And what you can look at, the data from the Beth Israel Deaconess Medical Center, large tertiary hospital in Massachusetts, and you can observe there's about 8% disparity. So men are far more likely to get a respirator than women. And the question is, of course, here you're going to ask, well, maybe men have higher illness severity, which for COVID actually is true. Well, if you adjust for everything else, so I put in illness severity, I put everything that I know about you demographically, and so on, you're still getting a large disparity. So even adjusted, there's a huge gap. Okay. Yes.
So maybe it's not a very question. What's big question? Everything I know about you demographically dictum.
Yes.
How do you know what is everything? Like,
No, yeah, everything available within the data, of course. We don't have genetic variations here, for example, but you have very good information. And of course, in intensive care units, you're being monitored very frequently in some sense.
you have a lot of features, can you talk about conjunctions of those features and so on?
I think so. And I'm happy to continue the discussion offline, actually, if you're interested in this example. And we don't have an explanation, by the way. Top clinicians in the world have no idea why this is the case. Okay, so I want to jump. Sorry,
What
yeah.
paper is that in? I don't see it.
What paper is this in? I can share a reference. I don't have a. Yes.
So just in this context, how do you differentiate between what is green and pink? Like what is okay by?
I'm not doing that yet. I'm going to do that in a second, actually. Yeah. Okay. Cool. I want to jump to a completely different context. I was just now in medical. I'm going to put my economics hat on, and I'm going to talk about something else. So here is some data from the US Department of Labor. And what you can see here, stratified across different levels of education, you can see what the average earnings are for men and women in the United States. This is from 2022. And what you can see there is that if you stratify by education and if you stratify by all other things that are available, right, what you will be seeing is that women earn less for the same job, adjusted for qualifications, adjusted for everything else. So this is this is from the US Department of Labor, right? So this is recent data. This is still out there. And for people who are in economics, this is not a surprise, right? I'm not saying anything new or claiming that this is a finding, right? People in economics are very aware of this. And what is another prominent example, and this is sort of a recent settlement in which a large bank agreed to pay a fine for redlining. So in short, what redlining, the concept of redlining, also well known in economics, the idea is that race can be sort of correlated with location of living, and banks, if they're using zip codes to decide on your loans, it can have a differential impact on minority groups. And as you can see here, and this is, I think this article is from 2022 or 2023, so it's last year or this year, this happens in reality, right? So we know that this stuff happens often. So what I want to say is that I've started with this picture of this cloud of the current world being sort of gray. My claim is this is not gray, this is very red. And I think this is what Cynthia was saying today. Bias is, if you open up medical data, economic data, bias is everywhere. I think there are some great examples in text data. I don't think usually about text data, but I find the applications very interesting. And what I want to say is this is 100% bias according to all the evidence that I've shown, and I'm not an expert, right? You can talk to the experts in all of these topics, and they would probably have similar evidence. And of course, if you're collecting data from this reality, even if you do it properly, and there are many sort of considerations in this setting, even if you do it properly, this data will collect, sort of have as an imprint this bias that exists in reality, right? And if you feed this into a machine learning system, and you're basically trying to learn what's in the data, you could be just copying over the existing world. And in some sense, what my claim is, we don't want to do this, right? We don't want to copy over the existing world. We don't want to learn the P star, right? Because P star in itself may be very bad and contains stuff that we really don't like as society. And instead, what we need to do, we need to change the current world and probably, hopefully, go in a direction which is more fair. And the question is, of course, how can we give some guiding principles about how this is to be done? And just to mention briefly, I don't want to dwell too much in the interest of time. I just want to mention that the law, for example, some of the things that I was mentioning. So within the law, there's this well-known concept of disparate treatment, which is used often in employment settings, and the phrasing of this concept is that if you were to change the protected attribute and keeping everything else the same, you shouldn't arrive to a different decision. So basically, this is causally trying to measure some kind of direct effect. And of course, the disparate impact doctrine is trying to talk about spurious and indirect effects, but I'm happy to discuss this offline if anyone is interested. And of course, the very last concept is sort of business necessity, which is important within the disparate impact doctrine. And unfortunately, in the interest of time, I will not be able to say a lot about why business necessity is relevant and how causality relates to considerations of business necessity. But in our paper, there are very detailed connections of these concepts. Okay, so before I continue, and of course, as a causal analyst, you have to see some graphs showing up. This is unavoidable, I think, or mostly unavoidable. And I have these three examples. I have this diagnostic delays example. I have the compass example, in which this is from criminal justice. I think many people working in fairness are probably familiar. And I have this census data example, in which you can, for example, measure the pay gap. And what it turns out, and this is, I think, sort of what we like to call a first order approximation of what's going on. So there's this model, there's this template model, which sort of fits quite well a lot of the examples that are out there. And basically what it turns out, you have some set of demographic variables, you have protected attributes that you single out. These two things are somehow correlated, for example, location of living and race or gender with other attributes and so on and so on. And of course, these two things affect a set of mediators W. So basically X and Z are pointing to W. This is what the arrow means in the graph. And finally, there's a specific outcome of interest that I'm trying to understand. And all of these variables are pointing to this outcome. Of course, people familiar with causality, and there are some in the audience, I think, will know that the assumptions are in the absence of arrows, but I don't want to go too deep. I think this is like an offline discussion for those that are interested, but bear with me for a moment and let me assume a graph like this. Okay, so what I want to say, and I think this is sort of the second main takeaway from this talk, is that if we have a setting like this, so we have this template model in which Z and W you can think of as multidimensional, so it's some kind of cluster diagram. And I give you some data, X, W, Z, and Y. The real research question I think that we want to begin with is saying, can we say anything about whether the current decision-making process is fair or unfair? So basically what I'm saying is we need to reason about whether something is fair before we even start to build machine learning predictors, and before we start to use AI tools to make decisions in the real world. And I think Frauke made an excellent point that it seems that once we have started building machine learning tools, we have only then went back and thought about this basic problem. And it's very true in, for example, in medical settings. And since fairness became a prominent field, people are thinking about the true sort of decision-making systems that are driven by human decisions. Okay, so this is the first task. And after this, of course, and I think this is where calibration is sort of very related, is you want to talk about the other setting in which you have a prediction and so you have a true label in reality, and then you have a prediction, and then you have data on your labels and on your predictions. And then there's again a question of whether this is fair or unfair, right? And now here is sort of the inflection point, is that what calibration is saying, calibration is basically requiring that you exhaust all of the variations from X into the label Y in the predictor that you're constructing. And basically, if you know that, for example, some part of this variation you don't like, or society would deem this variation as bad, being calibrated towards this can pose some kind of risk, okay? And I think these are sort of the two tasks that I like to distinguish, sort of bias detection or reasoning about fair or unfair without having any kind of a predictor, and in presence of a predictor. And sort of I want to be a bit more specific, a bit more concrete about what we can say from a causal viewpoint. So what I want to say is, and I think this is sort of the way we like to think about the problem, and I'm here focusing on the pay gap example that I gave. What I want to say is that if you take some quantity, so Y is in this case salary, and you look at the conditional difference between males and females in this data set. So if you think about this causal structure, right? If you think about what's going on in the real world, so what you can see is that there's some part of this difference that is driven by the direct effect. So in some sense, your protected attribute purely on its own causing a difference in the decision of your salary. You can also see that this conditional difference has a contribution from the indirect effect. So basically your attribute might be affecting something about your access to education or the work sector that you're in, and so on, which in turn affects your salary, right? So this is the indirect effect. And the third type of variation that we talk about, and this is somehow interesting because it's usually ignored in the causal inference literature, is actually the spurious types of variations. So in some sense, there's a specific contribution coming from these sort of backdoor pathways between the protected attribute and the outcome Y. Okay, so we have some kind of notion of a difference in conditional expectation, which breaks down into these three different parts. And what is interesting in the data that I have, actually the difference is about $14,000 per year. Okay, the average gap in the salary is about $14,000 per year. And the question is, what are these numbers, direct, indirect, and spurious for this specific data set, right? And of course, you can go and compute them in our current world, right? This is the data that is in the current world. This decision making is made by, right? These decisions were arrived to by humans. And what you can see is the direct effect is about $8,000. The indirect effect is about $7,000, and there's a minus 1,000 coming from the spurious effect. Okay, so this is what the current reality looks like. And now the question is really, are these values that we're seeing, are these values fair, right? Can we reason about whether these values are good, or can we say more about these values? And in particular, what you can notice now is there's some kind of societal consensus that needs to happen, right? We need to have a discussion, you need to have experts, you need to have people who understand causally or how this disparity came about, and you need to ask them, are the values that we have, are they good or bad in some sense? And one very typical one, which I've mentioned, is prohibited by law, is should there be any direct effect in this data set, right? Should you have any kind of variation in the salary that is not purely mediated by something else, right? And I think for the direct effect, I don't think this is, actually people are not very hard to agree on this one, right? We don't really want this direct effect. And what I want to emphasize here, I think that these types of judgments are hard to make if you don't consider the causal mechanisms that have brought about the disparity in the first place. So in some sense, I think causality can be a very powerful tool to help us understand what sort of disentangle what brought the disparities up in the first place. Okay, so the second setting, and here I think I want to sort of invite the people who are in the calibration research arena to sort of think about this in a causal way is the setting in which you have the true outcomes, sorry, the true observed label, and you have some kind of predictor. And first, as I noted, so this part is not under our control, right? So this is something happening outside, and the reality, we're not doing anything about this, right? We have no control over this setting. And what happens then is, as we said, we have quantified what the direct, indirect, and spurious effects are in this reality that exists. What we do have control over is the y hat, right? We are constructing something, and in the salary example, of course, predictions don't translate to decisions, but in the salary setting, it's pretty simple, right? If you have a prediction of the salary, you can just assign these salaries in reality. So there's a very straightforward leap from predictions to decisions, right? In this specific example, right? When it's probabilities, it's more complicated. But the question is, of course, if let's say that we predict these salaries and then we deploy them in a company, and by the way, people are doing this. This is not a hypothesized scenario. People are doing this. The question is at time t+1, what are we expecting to have, right? What kind of disparities are we expecting at time t+1? And I've labeled the disparity. So there's a corresponding sort of notion of direct effect for the predicted outcome, right, by hat, and I've labeled it psi1. So the question is, what should psi1 be, right? This is a legitimate question to ask. Do we want psi1 to be about 8,000 as it is in the original data, or do we want to have a reduced disparity along the indirect effect, right? And the same question naturally goes for the indirect and the spurious effects, right? So what should these values be? And what I want to emphasize now is that if you're thinking about calibration, the implication is that these values psi1, psi2, and psi3 will coincide with the reality. Okay, so this is what it means, right? To exhaust all of these variations from the attribute to the label, it means also that you will keep the values, the causal values, the causal effects will stay the same for the y hat as they are for the y. Now, what is a plausible alternative, and I don't think is a bad one, and many people I think would agree with this. Maybe we want to set the psi1 to be equal to 0, right? And what this means is we're not going to be calibrated any longer towards this psi1. But maybe in the psi2 and psi3, maybe you do want to you don't want to play with these variations. I'm not saying whether this is the right way to go. I'm just saying this is a possible alternative to this problem. But what I want to say is, and this is sort of like the main punchline, I think, from my talk, and I hope to get people interested in this direction, is it is possible, and this is what I want to say, it is possible to be calibrated only to a part of the whole story, right? So you can be calibrated with respect to the indirect or the spurious effect, but you don't have to be calibrated with respect to the direct effect, for example. And I'm going to now go into the formal result, and I'm going to share the reference for our paper, which we delve into this in much more detail. But in some sense, calibration is a very important part of fairness, but it's not the whole story. That's somehow the main takeaway from a causal analysis. Okay, so this is the main idea that sort of the second main takeaway. We can try to be calibrated towards the things that we don't consider as discriminatory, right? The stuff that we do consider as bad and discriminatory, we don't want to be calibrated towards them, right? Because that sort of takes this bias into the future time step as well. And I want to go through a formal result on causal calibration. I'm not very good on time. Yes, quick question. Yes.
Does it mean that, like, can we achieve psi1 equal to 0 by just adding $8,000 to salaries? Get direct D.
You can solve it in that way, but I'm not sure if that's how you want to solve it, right? Because you're sort of uniformly doing it across everyone. And I think in general, what I've been discussing with some people, it's sort of interesting to try to formulate new learning problems and new sort of paradigms that are trying to do stuff like this. This is what we're very interested in doing, if that makes sense. 5 minutes, cool. So I just want to mention the formal results on causal calibration, and I want to say what it roughly says. It's sort of in half an hour, it's sort of difficult to disentangle the exact sort of subtleties in this result. But what I'm starting with, there's this on the left here. I have this quantity which is trying to measure whether you're calibrated or not. So behind the bar, you have a fixed value of your y hat predictor, and you're changing the protected group from x1 to x0, right? And you're looking at this difference. Well, what it turns out it turns out that there's a way of doing a causal decomposition of this quantity. So in some sense, this quantity, which is just the difference, sort of trying to measure how calibrated or miscalibrated you are, it has causal variations within. And what you can get, and this is sort of the workload in our paper, is you can sort of find two terms and you can see what these terms correspond to, right? And I want to give you, I want to ground this, right? So basically this difference decomposes into two parts. And I want to say a bit about what these two parts are. So basically, if you think about a linear model, it's very nice to ground the intuition, I think, here, because people can sort of parse the result. So what the two elements are in this decomposition of this measure is the first element looks at, we sort of look at a fixed group of people in our data set. So we take people from group X1 corresponding to a fixed value of the predictor Y hat, and we take the analogous group X0 and Y hat. And what we're really measuring in the first quantity, we're measuring the causal effect of the protected attribute on these two groups, right? So this is a variation that naturally appears in this calibration measure. And what is interesting here is we're measuring the causal effect of the protected attribute in the true outcome Y. And what this means is that this is not under our control. So this is something that is happening in the real world, and the decision maker or the person designing the ML system has nothing to do with the first term. And I've just expanded here in this causal graph where the coefficients are sort of represent the linear coefficients of this system. Basically, what you can see, the first term is equal to the causal effect. So in some sense, the second term, which is in our control, is trying to offset this causal effect of the protected attribute. So in some sense, what you can see is you can see a causal story and a causal analysis of what calibration is trying to do. So for every causal effect that exists from the protected attribute to the true outcome, what you're doing when you're achieving calibration, you're trying to mimic this effect in your true outcome. This is how you can perceive calibration causally. And of course, I just want to say you can read this in Technical Report 92 on our webpage if you're interested. I think I've spoken to some people about this. Okay, good. So this is the formal result. I'm happy to take questions offline. I know that it's sort of packed in a short amount of time, but basically what I'm saying is calibration has a causal interpretation and causal implications, and this is the formal result in this direction. And just to conclude, I want to say how we like the broad framework, and I want to sort of point to some other problems that we are very excited about. So the way we think about this, we spoke a bit about this underlying reality, current reality that generates the data that we have. What our view is that we need to do some kind of causal modeling to understand the mechanisms that lead to these different disparities that we don't like seeing in our data. And we also need to think about like the norms that come from we need to think about societal norms. We need to think about legal regulations that are related to this. And then on top of this, we need to construct fairness measures, right? We need to be able to verify whether something holds in our data or not, right? And of course, empirically, we need to estimate this in the end, right? We need to do some kind of estimation, and I think someone else is talking about estimation in a second, which is sort of quite nice. But what I want to point to, and I think this is sort of a big distinction, which you can read more about in the paper, is that there are three different tasks that we see in causal inference. The first one is just bias detection, so you can even not have a machine learning predictor. You just need to see whether there's some kind of bias in your data. The second task is about fair prediction, and I think a lot has been discussed on this topic in this whole week. And the third one is fair decision making. And what I want to say is that calibration is very related to tasks 1 and 2, but it's just a part of these tasks, and there's much more that needs to be done, right? In sort of complementary to calibration in some sense. And fair prediction, I don't have time, unfortunately, to go through this, but fair prediction is trying to formalize some of the ideas that were here today, but we're thinking about a slightly different formalism in which we're trying to enforce some of these constraints, for example, absences of direct effects in the learning process and so on, right? So this leads to some kind of new formalizations of problems. And of course, so this is my favorite one. This is the one that I've been working on most recently, is how do you mitigate disparities over time? Okay, so you have diagnostic delays. How can we improve upon this? If there's someone sort of at Columbia University Hospital who wants to do this, how can we mitigate these disparities over time? And there's a lot of formalism going on. And I invite people, in section 5 of our paper, of the big paper that I mentioned, you can read about a lot about what we've been thinking. And we've spent 2 years on these problems now. Okay, and I just want to conclude in 3 lines. So first punchline, being calibrated, fully calibrated to a label that is sort of partly unfair may lead to perpetuating unfairness. Calibration clearly plays an important role. This is, I have no doubts about this. And it sort of is important in determining the size of the effect along causal pathways that are not considered discriminatory. This is what calibration is very helpful for. And as I said, just to conclude, it's part of the problem, but not the whole. And it would be great to sort of open up other research questions in this direction. And I think that's all for me. I hope I didn't cross the time too much. Thanks.
Time, let's
Sounds good.
other questions of